Hello. So this is our first lesson about sets, general notations, and we'll talk about the number sets too. Number sets of numbers. So about the sets, you need to know a certain type of operations which you will use in probabilities, and probably you've already seen them. So if I take a universe, sometimes it's called U, sometimes it's called omega, and in that universe I draw, this is a Venn diagram. If you don't know that, this is called a Venn diagram. The set A is like a part of the universe omega. It's the set of some elements in the universe. These are the elements I take in the set A, and these are the other elements of your universe. So the rest of the universe, the elements that are not in A, it's called the complement of A. You will find it marked a capital A with a line over it. It's called A bar, or sometimes it's called A with a little C here. It means complement of A. Sometimes it's called A prime. Depends on the books, but all of this is the same. So this is a set. You can see a set like a bag of marbles. So these are the marbles, and the set is the bag. So if you have an empty bag, if you have a set with nothing in it, it can happen. So you have your universe here. This is your set. I draw it smaller, but it doesn't have to be smaller. There is no size. So this is empty. This is empty, so it's called empty set, and the empty set is written like that, a 0 and a bar like that. We'll talk about inclusion. Excuse me, inclusion. So this is a subset. It means I have my universe here. In my universe, I won't draw the elements anymore. In my universe, I have a set, which is denoted A, or I will draw the elements, because with a subset, it's quite useful maybe. And in that set, I want to consider only these 3 elements. So this will be a subset of A. B is a subset of A. You will say B is a subset of A, or B is included in A, and the notation is this one, included in. So it's an inclusion. We'll talk about intersection next. Intersection of sets. So I can talk about intersection if I have at least 2 sets. It can happen with 3 or more, right? I'll show it with two sets. So this is always omega my universe. I have 2 sets. One is A, one is B. The intersection is the elements where A and B overlap. It means that these elements are at the same time in A and in B. So this means and. You'll see in the next part of this lesson that It's related to the logical operation called AND. So these elements are in A and in B. And you write it like that. It's called just intersection. The union of two sets is the word, well, represents the word or, except in math, or means or/and. So the union of A and B are the elements that are in A, or in B, or in both. So this means in math, when you have from a, I don't know, yes, for example, if you see an inscription like cheese or dessert, in math, it would mean cheese or dessert or both. And here the elements are in A or in B or in both. So the intersection is included in the union of it. Okay. This is denoted like that. It's called a union. And that's it. I'll erase the beginning. There is a very important property here that is very, very simple if you draw it. When you work with sets, you really need to make a drawing. It will make things really simple. If you try to just remember the formulas, it means if you need to remember them, it means you didn't understand them. So you probably have seen that in class already. Maybe you have seen these in your probability class, that the probability of A union B is the probability of A plus the probability of B minus the probability of A intersection B. Why? Because if you want to have A union B, your first idea will probably be to take the elements of A and the elements, this is this, and take the elements of B, this is this. But the problem is, you have counted this twice, once with the blue part and once with the red part. So you have to subtract it in order to count it only once. Okay, so if you make a drawing, and everything about the sets is really quite simple, quite natural if you make a drawing. I have to show you the notation, if you didn't see it in class already, for an element in a set. So we saw that A, if A is a set and B is a subset, I'll erase this. So if B is a subset, the notation for this is an inclusion. And the inclusion, the symbol for it is this. B is included in A. So you have to see that this is a set and this is a set too. It's just a smaller set, right? But if you look at the elements, like X is an element here, the notation is different. The notation is an E-like element. X is an element of A. So this is an element. It's like a marble in the bag of marbles. And this is a set. Of course, the negation of this would be B is not included in A, and X is not an element of A. This is the negation. Right. It will be very important that you really know the difference between these two symbols. In the exercises, you can't write one for the other, because you need to know if what you are talking about is a set or an element. Okay? We'll see these in the exercises. About sets, I'll finish with just the sets of numbers you use every day. So I'll erase all of this because I will need, well, you will use them, the sets of numbers, of course, and we'll need them to have examples for the exercises. So you have to, well, it's useful to imagine that your sets are like the Russian dolls. You know, the dolls where you have like the baby doll inside, and oh, sorry about my drawing, poor baby. And then the mother doll around it, and then the grandmother doll around it. And when you open the grandmother doll, you open the doll, you open it, and you find the mother, and you open the mother, and inside the mother, it's wooden dolls, you know. Inside the mother, you have the kid, right? So it's like that. It's very, very efficient to imagine it like that. So I'll draw the first set. I'm trying to make my Russian doll here. Okay. So I'll call it Z. It's the set of the integers. The integers are the numbers that can be negative or positive. I started too far, or 0, 1, 2, and so on. These are the integers. Inside the integers, you have the whole numbers. So the whole numbers are the positive numbers among the integers. Whole numbers. Which means I'm starting from 0 and taking only the positive ones. And here you have 0. I did the drawing like that because it's symmetrical. If you have the positives here, you can complete with the negatives here, and then you have the whole set of the integers. If you don't want 0 in your set, you write a star. It means 0 apart. It means that you take your set of the whole numbers and you take 0 away. It's everything in that set except 0. And it works with any set. If you write Z, with a star, it means the elements of Z except 0. After that, so you know that you can't always work with integers. So sometimes you have decimal numbers. It means you have a decimal part like 1.2. So these are the decimal numbers. So they have a decimal part, a decimal point. For example, because these means that it's a set. So I just give an example. 3.25, this is decimal number. because the decimal part stops. At one point, it stops, okay? It can't be infinite if you're in the decimal numbers set. Then you have the rational numbers. The rational numbers here, my doll is getting very strange shaped. So these are the rational numbers. Rational numbers. Which means that these numbers can be written as fractions. They are not always written as a fraction, but you have to know that the definition of a rational number is that it can be written as a fraction. For example, so you see that the green door is inside the orange one. It means that the decimal numbers, this set is a subset of the rational numbers. And it's very easy to see because this can be written 325 over 100. This is a fraction. When I say fraction, it means an integer over an integer, and b can't be equal to 0, of course, because you can't divide by 0, right? So the rational numbers can be written like that, but 3.25 is a rational number because it can be written like that. So this, maybe the last set you all know about, it's the real numbers. The real numbers. So here you have everything, included the rational. So you know that the red door contains the orange and the green and the black one. So I can say that like -3, -3 is a real number because it is inside the red one, okay? But some numbers are real numbers, but not rational. They're called irrational numbers, like pi, square root of 2, numbers like that. It has been proved that you can't write them like a fraction like that. And if you have heard about it, but you won't use it immediately, you have a bigger set here. You always have a bigger set around the last set you saw in any course in mathematics. You have a bigger set here, which is the complex numbers. So you have a real number plus I times another real numbers. So A is a real number. So here I use this notation is an element of, because A is a number, it's an element, and R is a set. And B is a real number. And the only thing you have to know about the number I is that squared, it's equal to -1, which is very strange because you have a number squared, which is negative. But still, we won't need it in this course, so I won't explain more about this, but if you have questions, I'll answer. So this is everything you have to know about the sets of numbers, and I'll make another video for the rest.